Thank you, Mr. Chairman. Good morning, everyone. I'm a postdoc research associate with Professor Jason Weiss at Oregon State University. I'll be discussing today the freeze-thaw performance of internally cured concrete. So I'll start my presentation with a general introduction, then I'll present the experimental procedure, the results we gathered, and I'll finish with a general conclusion. Internal curing consists of storing water in reservoirs inside the concrete. These reservoirs can either be porous bodies or superabsorbent polymers. After the setting of cementitious materials, the stored water can be released, reducing thus the shrinkage and increasing the hydration of cement particles. So the use of internal curing in concrete has shown benefit in increasing the resistance to early age cracking shrinkage, which will enhance the durability of the material. It has also been proven that internal curing mixtures perform well under freezing and thawing environment. For instance, we present here the results of the study of Ghantous et al. In 2013. So in this study, the internal cured sample were exposed to freeze-thaw cycle following ASTM 666, and then they look to perform as good as conventional mixtures as illustrated in this graph. So in this graph, we can see on the y-axis the average relative dynamic elastic modulus, and on the x-axis the number of freezing and thawing cycle. And this graph shows results for mixture with and without internal curing. All the results, as you can see, are similar. The lines are on top of each other. And that means that all the mixture performs similarly and resist freeze-thaw cycles. Also, in the study of Ghantous et al., we can see based on weight measurements, the middle graph in this slide, and then the dynamic modulus of elasticity measurements, the right graph, that internal cured mixtures with a low water to cement ratio perform better than intercuring mixtures with a high water to cement ratio. So in these graphs, the higher the line, the better the freeze-thaw performance. So we can see that the black line, which corresponds to the low water to cement ratio, have a better performance for freezing and thawing damage. And actually, in high water to cement ratio mixtures, the amount of water available is higher than the amount of water needed to replace the chemical shrinkage. This excess amount of water will be then unused and will keep the DOS of cementitious material higher than the critical value, and that will make the material more susceptible to freeze-thaw damage. That's why we can see that mixture with high water to cement ratio did fail freezing and thawing cycles. So all these results were collected at later age and prove that internal curing for cementitious material with a low water to cement ratio is good, and then the material will resist freeze-thaw environment. But the question we have is what will happen at early ages, and that's the objective of this study, where we are going to investigate the early age freeze-thaw behavior of internal cured cement-based sample with different water to cement ratios. So for the experimental procedures we used, we first start by preparing 8 different cement-based mixtures with varying water to cement ratio. So we have 4 different water to cement ratios, 0.3, 0.4, 0.5, and 0.6, with and without superabsorbent polymer. These mixtures were all sealed cured at 23 degrees Celsius for varying duration, 1 day, 3 days, 7 days, 14 days, and 28 days. After curing, they were immediately exposed to freezing and thawing cycle without any drying period. It's unlikely to be the case in the field, so results in this presentation should be viewed as worst-case scenario. And after the curing for all the mixtures, we characterize the freeze-thaw performance using length change measurements and then a conventional technique, which is the ultrasonic pulse velocity measurements. In addition, we measured the loss on ignition, and then from this value, we calculated the degree of hydration and the degree of saturation. So in the next slide, I'll be presenting how we did do the length change measurements and how we did do the degree of saturation calculation. So to start with the correlation of length change measurement with freezing and thawing damage, if we hypothesize that all the concrete pores are filled with water, when the temperature drops, some of the solution in these pores will freeze, especially the solution in the capillary pores and in the air voids. In addition, some microcracks will develop due to different pressure, osmotic, hydraulic, electrical, when the ice form. And then due to the increase in the volume of solution with ice formation and due to these microcracks, the length of the sample will increase, as you can see in this schematic. Now, when the temperature will increase, the ice will melt and then the sample will shrink in length again, but will never go back to its initial length. So we'll have a residual strain written here by delta epsilon, and then it can be calculated according to the difference between the initial and the final length of the sample, as shown in this equation. So this residual strain has been proven to be a good indicator for freezing and thawing damage. So as you can see in this graph, the samples with high DOS on the x-axis develop residual strain with positive values above 0, while samples with a DOS below a critical value, the residual strain will be equal to 0, which indicates the absence of freezing and thawing damage. To measure these length change, we use the thermomechanical analyzer. So this thermomechanical analyzer will continuously measure the length of the sample while being exposed to freezing and thawing cycles. So this machine has a cooling unit that allows the temperature in the chamber where the sample is sitting to go to negative values. As seen in this picture here, the sample is sitting on a stage and the probe is touching its upper surface. Length measurements are performed with an accurate LVDT, and then you can see that the temperature is decreased from 24 degrees C to minus 40 degrees C at a cooling rate of 1 degree C per minute, and is heated up to 24 degrees C at a heating rate of 1 C per minute, which makes the length of the test 2 hours only. And this procedure, we test a smaller sample with 10 millimeter diameter, 20 millimeter height. These can be conditioned fast to the value we want, and then we can test thus with this technique lots of sample in quick timing. In addition, to confirm the results we get from length change measurement, we did ultrasonic pulse velocity measurement on the same sample before and after freezing. And then we did measure the ultrasonic pulse velocity right before we put the sample in the thermomechanical analyzer and after we take it out, so after the freeze-thaw cycle. And then based on the equation here and in the reduction of the ultrasonic pulse velocity, we calculated the damage index according to the equation shown here. And then that's an indicator also of the freeze-thaw damage. So how does the results from the TMA look like? So if we look at a sample that's completely saturated, which is supposed to show damage because it has a DOS higher than a critical value, we can see on the y-axis the strain and the x-axis the temperature. When the temperature drops down, the length of the sample decreases until the freezing point where the ice starts forming. And then that's what we call the strain expansion. And that is determined by subtracting the strain at the end of the expansion from the strain measured at the beginning of the ice formation. Then when the temperature increases, the length of the sample increases as well until the ice melts and the sample shows reduction in length. So this reduction that we have here, that's called strain reduction and can be determined by first finding the inflection point of the curve, then determining the point A, which is the intersection between the vertical line passing by the inflection point and then the tangent corresponding to the curve before the melting. And point B, which is the intersection between the vertical line passing by the inflection point and the tangent corresponding to the curve after the ice melting. Then the strain reduction is just simply the difference between the strain measured at point E from the strain measured at point B. Then the temperature is increased again to room temperature, and the difference between the initial length of the sample at 20 C and its final length at 20 C allow determining what we call residual strain, which is an indicator for freezing and thawing damage. And then we will compare the values obtained from residual strain with the damage index obtained from UPV to be confident with the values we get from length change measurements. Now, if we look at the graph for a sample with a very low degree of saturation, almost dry sample, we can see that the strain versus the temperature follow a straight line, and that's because of the absence of ice formation. Now, to pass on the degree of saturation calculation, how we did do these values. So these were performed based on Powers model for all the cement mixtures tested in the study. So the schematic presentation on the left of this slide represents the volumetric phase volumes of cement-based sample without SAP addition, while the one on the right represents the volumetric phase change for cement-based sample with SAP. For each sample at each curing age, we took a small piece from the specimen, from the sample, and then we ground it and exposed it to drying at 105 C, then ignited at 2000 C. This allowed quantifying the amount of bound water, which was used to determine the degree of hydration. Knowing the degree of hydration, we calculated the degree of saturation based on Powers model, which we can see here the equation we used. So for samples with SAP in them, we accounted to the volume of water released by SAP and then the volume of voids that were generated after the water was released. So for both values, VSAPW, which is the volume of water released by SAP, and VSAP voids, which is a void generated after SAP releases the water, they are both there to compensate the chemical shrinkage. So they are equivalent to the volume of chemical shrinkage. Now let's look at the results we have. So we can see the degree of hydration obtained from loss and ignition measurements on the y-axis versus the curing age on the x-axis. The degree of hydration of cement-based sample with and without SAP with 0.3 water to cement ratio seems to increase from 1 day to 7 days and then remain relatively constant until the end of curing. The degree of hydration of cement-based sample with a higher water to cement ratio show a continuous increase from 1 to 28 days. So the cement samples with high water to cement ratio indicate a higher degree of hydration as compared to the sample with lower water to cement ratio, which is expected. And as we can see, if we look at the black curve and red curve, which are samples with low water to cement ratio below 0.42, we can see that the increase of the degree of hydration is more prominent than the other two mixtures with a higher water to cement ratio. For instance, for cement-based sample like the black and red one, the degree of hydration increased by 14% at 28 days of curing. So the takeaway from this slide is the benefit of internal curing is more visible in cement-based sample with low water to cement ratio. That's also visible in the degree of saturation measurements. So we have the degree of saturation on the y-axis versus the curing time on the x-axis. The black and red are 0.3 and 0.4 water to cement ratio respectively. Blue and pink are 0.5 and 0.6. So we can see that the degree of saturation of sample with low water to cement ratio is lower compared to the other one with high water to cement ratio. And then the dashed line here is the critical degree of saturation, which is the value that define when freeze-thaw damage will start. So you can see that samples with low water to cement ratio drop below this value earlier than samples with high water to cement ratio, which means that samples with low water to cement ratio will better resist freeze-thaw damage compared to samples with high water to cement ratio. And then we can see that the SAP addition to sample with high water to cement ratio slightly increase the degree of saturation at the different curing ages, while for samples with low water to cement ratio, the SAP increases the degree of saturation only at early ages, but it does even decrease it at later ages. Now, if we want to do a more direct measurement for freeze-thaw damage, we will be comparing the residual strain we measured based on length change measurements versus the damage index obtained from UPV to just be more confident with the results from TMA. So we can see that when the length change measurements show a damage residual strain higher than 0, the UPV measurements show also damage. And then when the UPV does not show damage, the residual strain have a value below 0 also, which indicates the absence of damage. We can then confirm based on this graph that the residual strain is a good indicator for freeze-thaw damage, and we will use this parameter, the residual strain, to look at the freeze-thaw damage for samples with SAP. So if we go ahead and look at that, and we start with mixture with a low water to cement ratio below 0.42. So we have 0.3 water to cement ratio on the left, and 0.4 water to cement ratio on the right. We can see on the y-axis the residual strain, and on the x-axis the curing time. As visible, the residual strain decreases with the curing age in both cement-based sample with and without SAP, and there was even no measurable residual strain in cement-based sample with water to cement ratio of 0.3 for the entire life of the specimen, which is a filled dot in the left graph. For cement base with water to cement ratio of 0.4, the right graph, a positive residual strain was recorded at 1 day of curing. However, no residual strain was measured at later ages. For cement-based sample with SAP, positive residual strain are recorded at 1 and 3 days of curing respectively for both water to cement ratio. That means that a curing period of more than 3 days is needed to prevent freeze-thaw damage in internal curing paste with a water to cement ratio below 0.42. So the SAP addition slightly increased the freeze-thaw damage at the very early age, less than 3 days, for mixture with a water to cement ratio below 0.42. So care should be taken by avoiding freezing and thawing cycles for these mixtures just during the first days, 1 day and 3 days. Now, if we look at higher water to cement ratio, 0.5 on the left graph and 0.6 on the right graph, we can see that for 0.5 water to cement ratio, we have positive residual strain for both matrix with and without SAP. And then on the right graph, we have high residual strain, higher than 0 for both mixture for the entire life of the sample, up to 28 days, what we tested in this study. And this means that SAP does increase the curing period needed for mixture with high water to cement ratio to resist freeze-thaw damage. For example, for 0.5 water cement ratio, the sample without SAP does show negative residual strain or around 0 at 14 days of curing, while when we add SAP, the residual strain stay positive, which means freeze-thaw damage exists up to 28 days of curing. So the takeaway here is that the SAP is not recommended to be used for high water to cement ratio, but it does not impact the low water to cement ratio. So if we summarize the data we've been looking at in this slide here, we have the minimum curing duration needed to reach a residual strain below or equal to 0, absence of freeze-thaw damage on the y-axis, versus the water to cement ratio on the x-axis. In black, we can see the values for plain cement, and blue the values for samples with SAP. Can be concluded the addition of SAP in the matrix with a water to cement ratio below 0.42 slightly increases the curing duration needed to avoid freeze-thaw damage. And the addition of SAP to mixture with high water to cement ratio is not recommended. To conclude, internal curing works well for materials with a low water to cement ratio by first increasing the degree of hydration, reducing the cracking potential, and when properly designed, internal curing mixture with a low water to cement ratio will be freeze-thaw resistant. And then care should be taken to avoid freeze-thaw damage during the first few days of curing, which means that internal curing lower freezing and thawing resistance only at very early ages, the first 3 days of curing. So that's all. These are for low water to cement ratio. Thank you for your attention. I'll be happy to discuss any question you have.
Thank you, Rita. Have you done work in concrete to show internal curing of mixtures with water cementitious ratio of 0.4 is not compromised?
So the materials we tested in this study were all cement paste at early age, but the materials that were tested by Jones et al. Were at later age, 14 days of seal curing. This one does show that 0.36 is not compromised, 0.42 resists better than 0.48 and 56. If you can see my slide.
Okay, thank you. We have a second question. Do you expect similar results with lightweight aggregates instead of SAPs?
So, since in this study we were doing cement base, we haven't used lightweight aggregates. And then if we do that, I think we should expect similar results, because if we will be using mortar or concrete, we'll have less volume of base, so we should be expecting less freezing and thawing damage.
Okay, we have time for one more question. Do you plan to extend your paste work to concrete?
That's not a plan for internal curing. We're working in concrete for other study related to freezing and thawing, but not for internal curing.
Rita, thank you very much.